Good day, I'm Jhon Lloyd Bongat. Together with my groupmates Gerald and Omie Jabla, we will be presenting our final term PIT on engineering economics. We chose to focus on the agriculture sector, specifically on a vertical farming problem with an environmental control system as the solution. We will start with a definition of terms.
Engineering economics is a branch of economics that applies economic principles to assess the cost and benefits of engineering projects. It involves evaluating the financial feasibility of decisions by considering factors such as the time value of money, cost-benefit analysis, net present value, and internal rate of return. Through these tools, engineering economics helps engineers and decision makers make informed choices about resource allocation, project selection, and process optimization, ensuring that projects are not only technically sound but also economically viable. Vertical farming is a method of cultivating crops in vertically stacked layers or vertically inclined surfaces, often within controlled environments such as indoor facilities, warehouses, or skyscrapers. This innovative approach to agriculture utilizes vertical space to maximize crop yields and efficiency. By employing technologies like hydroponics, aeroponics, and LED lighting, vertical farming aims to provide a controlled environment for plant growth, optimizing factors like temperature, light, and nutrient levels. This method offers advantages such as reduced reliance on traditional agricultural land, conservation of water, and the potential for local or urban food production, minimizing transportation cost and environmental impact. Vertical farming holds promise for addressing food security challenges in densely populated urban areas and promoting sustainable agricultural practices. How is engineering economics relevant in agriculture? Engineering economics is vital in agriculture as it enables a systematic evaluation of the economic viability of technological interventions. By assessing factors like initial cost, operational expense, and expected returns, you can make informed decisions on technology implementation, optimizing resource allocation, and ensuring sustainable agricultural development. This approach enhances financial stability and contributes to the sector's long-term success.
Now we will be moving on to our problem. Our problem deals with crop yield inconsistency in vertical farming. Vertigrow Gardens has a growing concern about the inconsistent crop yields in their vertical farming systems. Vertical farming, once considered a futuristic solution to urban agriculture, is facing challenges due to varying environmental conditions within the vertical stacks. This has led to unpredictable crop yields and increased operational costs. The proposed solution to this problem is an optimal environmental control system. To address the issue of crop yield inconsistency in vertical farming, engineers propose the implementation of an advanced environmental control system taking into account engineering economics concepts. Step 1 of our solution is the initial investment. Installing sensors and monitoring devices throughout the vertical farm costs 50,000 pesos. Implementing an automated climate control system costs 100,000 pesos. Upgrading the lighting and irrigation system for better efficiency costs 75,000 pesos. The total initial investment is 225,000 pesos. Step 2 of our solution is the operating costs per year. The maintenance of sensors and monitoring devices costs 10,000 pesos. Energy costs for the automated systems cost 30,000 pesos. Routine maintenance and inspection costs 15,000 pesos. The total operating cost per year is 55,000 pesos. Step 3 is benefits and profits. Improved crop yield consistency leads to an average 20% increase in harvest. The resulting harvest is 200,000 pounds per year. Higher quality crops also result in a premium price increase of 15%. The price increases from 1.50 pesos per pound to 1.73 pesos per pound. The total additional revenue can be solved by multiplying £200,000 per year multiplied to 1.73 pesos per pound, which equals to 345,000 pesos per year. In step 4, we calculate the net profit. Net profit equals revenue minus total operating costs. Our total revenue is 345,000 pesos and our total operating cost is 55,000 pesos. To get the net profit, 345,000 pesos is subtracted by 55,000 pesos. The result is 290,000 pesos and that will be our net profit. Step 5 is return on investment or ROI. To get ROI, the net profit is divided by initial investment. Our net profit is 290,000 pesos and our initial investment is 225,000 pesos. 290,000 pesos divided 225,000 pesos results to 1.2888. This value is then multiplied by 100 and our ROI will become 128.89%. By implementing the optimal environmental control system, the vertical farm in Vertigrow Gardens not only increased its overall crop yield, but also improved the quality of the produce, resulting in a substantial increase in revenue. The initial investment in the ECS pays off in the long run, with a high return on investment of 128.89% and a more sustainable and profitable vertical farming operation.
In the provided solution, the economic concepts used are: first is return on investment or ROI. This concept measures the profitability of an investment relative to its cost. It is calculated as the net profit divided by initial investment expressed as a percentage. Second is cost-benefit analysis. The solution involves assessing the cost, both initial and operating, against the benefits: increased crop yield, higher quality produce, and additional revenue, to determine the feasibility and profitability of the proposed solution. Third is revenue maximization. The solution focuses on optimizing crop yields and improving the quality of produce to maximize revenue. The principle is based on economic concept that higher quality products can often command higher prices in the market.
And the last one is economies of scale. The proposed solution involves implementing a more efficient and automated system to control environmental conditions. This aligns with the economic principle of economies of scale, where larger scale operations can often achieve cost savings and increased efficiency. These economic principles are commonly applied in engineering economics to make informed decisions about investments, operational improvements, and resource allocation. This will be the end of our presentation. Thank you for watching.